Big Brains is supported by UChicago's Leadership in Society initiative, which guides accomplished executives in transitioning from long-standing careers toward purposeful next chapters of leadership for society. Your next chapter matters. More at leadershipforsociety.uchicago.edu. There's no shortage of news reports or documentaries about how climate change is destroying the world as we know it.
It's been a week of record-breaking heat around the world. The grim milestones are the latest in a series of climate change-driven extremes.
A steady and constant drip of stories about our impending crisis.
Triple-digit temperatures for days on end. Smoke from record-setting wildfires fouling the air. Warming oceans, bleaching coral reefs.
It can all start to feel a bit overwhelming.
For some people, it becomes an overwhelming sense of despair or anxiety. Psychologists call it climate anxiety.
The challenge with climate is that we really must fix it because climate will just keep getting worse. If we really do nothing, it really is terrifically damaging.
That's renowned scientist David Keith, a professor in the Department of Geophysical Sciences at the University of Chicago.
But at any given time, there really isn't any reason to especially work to fix it today. And so people try and create reasons, like they say we want to keep under this threshold of 1.5 C, or we must do it by this meeting. But the geophysical reality is it just this cumulative drip, drip, drip of things getting worse.
You often hear if we could just convince governments and companies to cut emissions, we could solve this problem. But I hate to be the bearer of bad news. It's worse than that.
Climate also has the following really bad problem, that it's cumulative. That the amount of climate change we have is basically proportional to the cumulative emissions of carbon dioxide over all historical time. And that means that even if you eliminate emissions, you don't make the problem any better. You've just stopped it making it worse. Because just cutting emissions, which is very hard to do, but doable, cutting emissions doesn't kind of instantly make things better.
So what are we supposed to do? Is this just a hopeless problem? Keith says no. He has spent a significant portion of his career studying an out-of-the-box solution, something called solar geoengineering.
Solar geoengineering is the word that's used for the idea of humans deliberately making the Earth a little bit more reflective to, in the short term, reduce some of the risks of carbon dioxide.
And if the models and science are right, this really could be a crucial part of solving the climate crisis. So if you're wondering why you've never heard of this before, there's a reason. Although the idea is fairly well known, it's so controversial that some scientists think we shouldn't even be talking about it.
It's certainly controversial. All these ideas of solar geoengineering are controversial. I think the underlying reason is a sense that they will distract us from doing what we should do to cut emissions. The idea that it's kind of a band-aid that would not just be used in a good way to deal with a wound while you seek other care, but a band-aid that would distract you from seeking other care at all, or something that would be exploited by political interests of big fossil fuels or what have you to avoid doing the work needed to cut emissions.
But given the trend of emissions and their permanence in the atmosphere, Keith argues that we need to at least be researching solar engineering as a possibility. And he recently joined the University of Chicago to be the director of the Climate Systems Engineering Initiative, in which he hopes to push this research forward.
Because there has been so much criticism and research in this area, I expected a lot of criticism, and I have heard very little. Not zero, but very small. And I think there's a way in which I sometimes think as I get older, I'm fighting last year's battle. And one of the things I've noticed with this program at UChicago starting up is how people may have different opinions about exactly how to do it. Of course, that's healthy, but almost nobody I talk to thinks that it's wrong that we're doing it.
Welcome to Big Brains, where we translate the biggest ideas and complex discoveries into digestible brain food. Big Brains, Little Bites, from the University of Chicago Podcast Network. I'm your host, Paul Rand. On today's episode, the pitfalls and possibilities of climate systems engineering. Well, why don't we just start with maybe a basic question of, first off, how in the world did you start getting interest in wanting to work with the climate?
In the late 80s, I was a grad student in physics at MIT, and I really just fell into some friends who were working on climate. And I got invited to this kind of amazing bottom-up group of graduate students between Harvard and MIT working on both the science and social science aspects of climate, or global change as we were calling it then. And I think I'd come from an environmental background. My parents were environmental scientists, so maybe I was sort of looking for something outside physics that was more interesting, that mattered more to the world, that mattered in a way that mattered to public policy. And I thought that climate was amazing because it both had these first order public policy implications and it had these huge first order uncertainties, which I really found wasn't true in physics. So in physics, I worked on a thing called an atom interferometer, and it was a big hit. It was I was lucky to have a great PhD project. But in some sense, my PhD project was trying to prove de Broglie's, I don't remember, around 1916 thesis. And never for a second when that experiment was not working did I think that maybe de Broglie was wrong. It was a way in which it was just clear we were demonstrating something that we basically already knew the answer to. We weren't really asking, from my perspective, a deep question about how nature worked.
You're validating.
Yeah, whereas for climate, there's lots of deep questions. The first thing I worked on was just trying to measure the heat flow from the equator to the pole, and we didn't know that to better than a factor of about 2.
Well, at what point did you come up and look at this and think there's something involved with climate systems engineering? And can you give me a top-line definition of climate systems engineering, which is a good thing to have before we talk about how you actually got into it?
Well, climate systems engineering is a new UChicago word, and I think it 2 main components. One is solar geoengineering, which is this idea that humans might deliberately try and make the Earth a little bit more reflective by some technological means, like putting aerosols, tiny particles in the upper atmosphere, or making the ground wider, or a shield in space, and do that as a way to offset or reduce some of the climate risks that come from accumulated carbon dioxide. But the other thing that's in our climate systems engineering program at UChicago is the open systems part of carbon removal. So that is removing carbon from the atmosphere by manipulating land ecosystems, by trying to accelerate weathering, or a bunch of related ideas that are really about kind of manipulating the Earth system to get more carbon out of the atmosphere.
When I see things that are being talked about that fit into this mold, examples I've seen are things like space mirrors or salt crystals to brighten low-flying clouds or fertilizing the oceans with iron. That sounds like some pretty serious science fiction that's cooked into this. Is it real?
Well, what does sounds like science fiction mean? So if you were sitting around in 1900, looking at how you were going to have the population run out of the ability to grow because there wasn't enough fertilizer and not being able to make enough explosives, you would have thought it was science fiction to take regular nitrogen from the atmosphere and make fixed nitrogen, the Haber-Bosch process. And yet that process is probably, in some ways, the most important single industrial process that humanity has ever developed. So science fiction can mean a lot of things. It could mean that it's politically infeasible or technically infeasible. Science fiction is a kind of pejorative term that might mean that something is technically hard or that it's politically hard or unlikely. Carbon removal and solar geoengineering are kind of science fiction in opposite respects. So some kinds of solar geoengineering are so technically easy that even the strong critics don't argue that they're impossible, but they argue that they're politically infeasible or destructive. Whereas for carbon removal, it's almost exactly the opposite. I think there's very broad agreement that if we had cheap, safe carbon removal, we'd take it, but it seems like science fiction to make it cheap and safe.
Keith has worked in both these areas, but we'll start with solar geoengineering. And the main plan he envisions to make this work would be to release sulfates into the atmosphere to cool the planet. So here's what this would look like. Picture a fleet of airplanes, about 100 or so, flying across the sky, dispersing 2 million tons of sulfur per year into the stratosphere. Those sulfates would combine with water vapor to form aerosols covering the world in a haze that would reflect solar radiation away from the Earth, leading to...
Well, the benefit would be reduced climate change, so cooler temperatures, less extreme storms, less sea level rise, etc.
And the idea would be that it's going to reflect sunlight back into space. And what percent of that sunlight being reflected back do you think has to be done for this to be impactful?
There's no threshold. So even if you did 0.1%, you would have some impact in reducing climate change a little bit late in the century. I think if you wanted to shave off something like half a degree or a degree in the latter half of this century, so not necessarily cooling it down, but reducing the warming, say from 2.5 to 1.5 degrees later this century, then I think you're talking about something a little less than 1%.
And if we accomplished that amount of a little less than 1%, what kind of impact would you expect that we would actually see?
The really surprising result of the last decade or so of research is that if you did it pretty evenly, uniformly, north and south and east to west, and if you did it with some relatively safe choices of aerosols, it looks like, according to the models, but they're the same models as we have to predict the impacts of climate change, it looks like the impacts would be beneficial almost everywhere, and that the negative impacts would be comparatively quite small, like 100 times smaller than the benefits. We're talking about saving 1 million lives a year late this century.
And it would be relatively cheap, costing anywhere between $5 to $10 billion a year.
And the economic benefits are huge, and they come most to the world's poorest. So in the one study that looked at the distributive impacts of climate change on the economy, it did more to cut the income inequality between countries than almost anything else you can imagine, because climate change reduces growth rates in hot countries. So it's a huge benefit.
Okay, so sulfuric acid in the stratosphere, a constant haze covering the globe. You wouldn't be wrong to ask, couldn't this have disastrous side effects?
So we're just finishing a study now where we can compare quantitatively the air pollution harms from people who would die from that sulfate pollution, and you can compare that to the benefits of people whose lives would be saved by having less heat deaths, and the benefits are of order 100 times bigger than the harms. Now, I might be wrong. It's early days. I'm not advocating deployment. And I think that's the weird social paradox of this, that on the one hand, it's this kind of taboo, almost nobody wants to look at it, it looks very scary. On the other hand, there really is quite a lot of evidence that it could substantially reduce climate risks, and especially in ways that benefit the world's most vulnerable and poorest people. And that's a huge win.
What side effects do you have the most potential concern about?
Well, the obvious ones that people worry about are damage to the ozone layer, or obviously people who haven't looked at it technically worry about acid rain or about air pollution impacts, because we know that sulfuric acid is an air pollutant and causes acid rain. But in fact, quantitatively, it doesn't seem like that's either of those things are much of a concern. So I worry more about the things we don't know so well. I worry about unexpected things that would happen in the upper part of the troposphere. This is the well-mixed atmosphere high in the tropics, but below the stratosphere, which in the tropics starts at about 17 kilometers or so.
As you're talking, it's reminding me of a scene in Oppenheimer where they're getting ready to test, and the question is, well, what do you think are the risks? It's like, well, we don't know. We're not sure what's going to happen when we do this.
Yeah, another podcast host, I was on a podcast, Elizabeth Colbert, that asked that question. I think it is in many ways a deeply incorrect analogy, and here's why.
Go ahead.
The worry that you see in Oppenheimer was the worry that the bomb would actually create a chain reaction in the atmosphere, make the atmosphere fuse in a way that would blow up the whole world. And there were some early calculations that suggested that was possible. By the time they did it, they were very confident it was not. There's some deep way in which adding sulfur to the atmosphere cannot be like that. And the reason is that we already do add an immense amount of sulfur to the atmosphere.
Interesting.
So at the peak of pollution, humans were adding 100 million tons a year of sulfur to the atmosphere. And to cool the world late this century, the kind of amount I would think might be reasonable, we'd be adding 1 or 2 million tons a year. So 1 or 2% of what we added. And there's just physically no possibility for a chain reaction that way. That's not to say there's no risk and there are no problems. I think a deep fact about climate engineering is it's really doing some things that effectively are a lot like natural processes that already happen. So we've already seen big volcanoes, like the Pinatubo volcano, put 8 million tons of sulfur in a single year.
My goodness.
So you know that if Pinatubo put 8 million tons and you go do an experiment that puts a ton, it just can't be that experiment blows up the world. Otherwise, the world would have blown up with Mount Pinatubo, or in fact, a much earlier volcano. The issue is how we improve the science to do better at predicting what the risks are and at what the side effects would be, and also how we invent slightly different ways to do it. But there's a way in which that is quite different because it's not an encapsulated technology that works or doesn't. It's a way of intervening in nature that will for sure have unintended side effects. That's important to say. No version of solar geoengineering will work perfectly the way people think, but it still might be that it's enormously useful. What needs to happen is an enormous amount of research building on the backs of this breadth of atmospheric science. So little experiments to understand the way sulfur would coagulate in aircraft wakes, little experiments to understand how marine clouds could be made a little whiter by putting sea salt particles into them, little experiments to understand how cirrus clouds might be thinned and how they relate to aircraft contrails. And all of those are kind of applying pieces of existing atmospheric science to this new goal of humans consciously and deliberately intervening in the Earth system to reduce their footprint.
But there are concerns beyond just the effects of solar geoengineering on the environment itself. That's after the break. Have you ever wondered what goes on inside a black hole? Or why time only moves in one direction? Or what is really so weird about quantum mechanics? Well, you should listen to Why This Universe. On this podcast, you'll hear about the strangest and most interesting ideas in physics, broken down by physicists Dan Hooper and Shalma Wegsman. If you want to learn about our universe, from the quantum to the cosmic, you won't want to miss Why This Universe, part of the University of Chicago podcast network. Big Brains is supported by UChicago's Leadership in Society initiative, which guides accomplished executives in transitioning from long-standing careers toward purposeful next chapters of leadership for society. Your next chapter matters. More at leadershipforsociety.uchicago.edu. Keith views solar geoengineering as one piece of the climate solutions puzzle. Any viable plan would have to include cutting emissions as well, but there is a problem doing both at the same time. If solar geoengineering could mitigate the effects of emission, companies and governments would be incentivized not to worry about cutting emissions. This is the moral hazard of solar geoengineering.
So I think the biggest concern is the moral hazard concern, the idea that just talking about these things will reduce the pressure to cut emissions and get us into a deeper problem by putting more and more CO2 in the atmosphere because we didn't cut emissions.
Because people will say, it doesn't matter, we'll just take these steps and that'll fix it.
Or more directly, because political forces that don't want to cut emissions, meaning fossil fuel dependent nations or big fossil driven companies, will exaggerate how well these technologies work to argue that we shouldn't be cutting emissions, and that they will succeed in that argument by slowing down emissions cuts. That is the fear. Mm-hmm. To be clear, I don't think the moral hazard conversation is necessarily a reason not to do it or a reason not to do research. There are lots of examples of these moral hazards or risk compensation in public policy, and they don't mean we shouldn't do things. There were people who argued strongly that we should not put airbags in cars because they would encourage more dangerous driving, or that we should not...
Or seatbelts.
Yeah. I think that we should think hard about political exploitation. Then there's a bunch of sort of procedural justice issues, like who gets to make the decision.
Okay.
And there's distributive justice issues, like who's harmed and whose benefits. And there's issues of kind of taking control of of nature, where people have really mixed feelings about the idea that humans should intervene in the natural world this way, even if the goal of intervention is to reduce the human footprint on nature.
But one thing Keith makes absolutely clear: taking it seriously and researching it is not the same as advocating for it.
I'm definitely not advocating that we do it today. Indeed, I would advocate for countries articulating some kind of moratoria against immediate deployment.
And why is that?
Isn't it obvious why a moratoria? I mean, why moratoria? Because there's a danger of chaos if some countries just decide to start doing this. Because we really don't have a political mechanism that's sufficient yet to make informed, plausibly consensual decisions about how it gets done. The big hook. My friend and revered colleague Oliver Morton wrote a beautiful book about this, one of the best books. And he is very careful to avoid using the word we, because he says it sweeps under all the hard problems. It's natural to want to say it, and I say it too. I'm not criticizing you for saying it. But of course, the whole challenge is we don't live in a world with one we. There are billions of people and billions of people who don't exist yet but will exist, who have different values and make different choices. So there's no way the world makes a single choice. It's just not how the world works.
And because it's so simple and cheap, any country could unilaterally make the decision to implement this plan, and it wouldn't take long.
I mean, not quite the next day, but if you're willing to do it a little lower in the atmosphere with existing commercial aircraft, it would be plausible to start in just a few years.
But if this is dangerous enough to put a moratorium on implementing, why study it at all?
We keep coming back to the politics of this, politics of moral hazard, politics of North versus South, etc. But it's important to try and separate, not that they're ever totally separable, the science and the actual human and environmental trade-offs from the politics. One of the ways to do that is imagine a kind of thought experiment. Like imagine that humans had never emitted CO2. We, went directly to solar power or nuclear power. But that then there was some big geologic event, outgassing from the Earth's crust, that was releasing carbon dioxide in exactly the amounts that humanity's now releasing it. And that geologists could be confident that this event would keep releasing it with exactly the amount that, say, one of these IPCC scenarios suggests. So then we'd have all the same climate problem we actually have, but humans wouldn't be the cause of it. And we'd still have the chance to remove carbon from the atmosphere with carbon removal, and we'd have the chance to do solar geoengineering, and we'd have the chance to do local adaptation, of course. But emissions cuts would be irrelevant because it wouldn't be our emissions. So I think in that world, solar geoengineering and carbon removal would look utterly different, because you wouldn't be dealing with, well, we really should cut emissions. You'd be dealing with what are the trade-offs between doing these things with the various risks and consequences they entail and not doing them with the risks and consequences that entails because the world keeps getting warmer. And I'm not saying that is our current world, because in our current world, we are responsible for emissions and we must cut emissions, but we can't cut them instantly. So I think thinking about that world is useful because it forces us to think about the real trade-offs over the next decades of who would benefit and who would be hurt by using these technologies. How would the impacts be on ecosystems, which are the questions we ought to be asking, and separates that a little bit from the questions of what we ought to do to drive emissions cuts, which we should be driving faster and we are doing. Everybody wants to think those problems as totally intertwined, and I think they're a little more separated than people think. I think the ethics of and the science of whether or not we should do solar geoengineering is significantly decoupled from emissions cuts. That is, I think the questions about doing it or not doing it actually would be about the same if emissions were cut to zero today as where we are. And that's not how most people think about it, but I think there's some truth there.
As you look at what is happening technologically and politically, where does that take you in terms of the likelihood that some of these methods will actually see the light of day in usage?
Nobody knows. And I think an answer that I put a lot of stock into is I think that people like me are probably particularly bad in some ways at guessing how they'll be used. There's wonderful evidence from this guy Tetlock, who's written these super forecasting papers and done studies that shows that for things like this, I think sometimes people who are generalists and farther away may be better judges than people who are specialists and too close. So I could imagine anywhere from the beginning of real deployment of solar geoengineering in a decade from now to a real kind of sticky moratorium where it's not deployed through this whole century. Those seem to be both possible outcomes.
Solar geoengineering isn't the only form of climate systems engineering that Keith does. As we discussed earlier, he's also working on the second science fiction type climate solution, carbon removal.
Carbon removal is just the idea that people could reverse the process that got us into this mess. So the process that got in this mess was burning fossil fuels. That was carbon that was long isolated from the biosphere, carbon from the geosphere, if you like, underground, coal and gas and oil.
And typically that's done how?
Well, there is no typically. This is, more or less a new idea. Early on, I worked on assessments of two carbon removal technologies.
One was what's now called BECS. Biomass was CO2 capture and storage. And me and a graduate student, Jamie Rhodes, I think wrote one of the very, very first papers on BECS. And then I did a lot of effort behind the scenes in the IPCC special report on CCS to kind of get BECS embedded into the kind of assessment system. And it's now one of the big things people talk about for carbon removal. But then kind of by chance, when I was at UChicago and founded this company that was doing direct air capture, a company called Carbon Engineering, and that subsequently actually grew to be a pretty big kind of 160-person company, and it's now in the process of being sold to Occidental Petroleum, and there's actually a 500,000 ton a year plant that is being built as we speak, kind of, of order $1 billion of capital really going into the ground, which is very exciting.
Wow.
We've kind of left direct air capture out of the kind of initial idea of what UChicago would study because it's not open system carbon removal. It doesn't involve this kind of complicated interdisciplinary geo and environmental science. But from my perspective, there's another reason. I really want to avoid conflict of interest. So was very conscious after I founded Carbon Engineering. I never did any more academic work on the topic. The only time I published a paper about the company's work, it was very clearly used the company's address under my name, not Harvard's. But it's also important to say that from my perspective, I don't see the Climate Systems Engineering Initiative doing any serious work on direct air capture. So from that respect, it's pretty separate from the work I did founding that company. And then now at UChicago, I'm really changing gears because the UChicago Climate Systems Engineering Initiative is looking really at three things: at solar geoengineering, at open system carbon removal, and at some of these ice sheet interventions. And so open system carbon removal to us means ways that humans somehow intervene in the natural system in ways that do permanent carbon removal. So there are really two technologies that we're thinking about the most.
Okay.
One is enhanced rock weathering, which is the idea that you grind up basaltic or basic rocks and put them in agricultural soils where they would weather. Weathering is just the natural process by which rocks break down, and the ions, the constituents of the rocks end up in the ocean. And these rocks are bases, and high school chemistry is CO2 is a weak acid, and acids and bases want to find each other and make salts. And so the long-term way nature will get rid of the CO2 we're burning is that the natural rocks will weather, and they will produce these basic ions, which go to the ocean and balance CO2, and then the CO2 is effectively removed from the Earth system. That's what will naturally happen anyway, is naturally happening. So the idea of enhanced rock weathering is to accelerate that natural process by grinding up some rocks that we know are the right kind of base and putting them on agricultural soils where they're kind of aerated, there's microbial action and exposure to water and air, and they then have these weathering reactions. There's another set of ideas which are sort of very similar. They're taking some of the same materials and putting them directly in the ocean. And indeed, that's called ocean alkalinity addition, to really get these basic ions, cations, into the ocean where they will restore the ocean. That is, the ocean now is being made more acidic by CO2. So you'd be adding bases, you'd be bringing the ocean back to the pre-industrial natural pH of the ocean, and you'd be permanently removing CO2. So there is more than 1 million tons a year of commercially claimed removals happening this year by enhanced rock weathering. There's a whole bunch of companies that are actually out there in the field getting this done.
Fascinating.
As one of the participants told me, it's sort of frighteningly easy to start one of these companies because you basically need a granite mine or whatever. There's some other minerals as well, and a ball mill to grind this stuff up small. And then you just pay farmers to use equipment they already have to distribute this stuff on soils. And that is happening very fast in some places. So I think there's a big need for academic researchers to understand better how well it works, because the companies obviously have a self-interest in claiming it works really well. And it's actually hard to know how much carbon is being removed and what the environmental impacts are. The companies want to tell you this is all both a benefit in removing carbon and a benefit for agricultural soils. And I think in some cases that's going to be true. But in other cases, there's going to be harms to the environment or harms to the soils. And we need to understand that better. Those are the two most obvious ones. But to me, open system includes a whole series of things, including kind of frightening high-tech things. So there are groups of researchers, some at Salk Institute, who are working very seriously on genetic modification of some crops to make the roots either penetrate deeper or the lignin. Lignin is the kind of material that holds cellulose together. It's the kind of sticky compound in plants. And if you make the lignin more recalcitrant, is the buzzword, which basically means it breaks down less in the soil, then you tend to get more carbon in the soil. So if you had plants that make this more recalcitrant lignin, you'll build up soil carbon. Again, in general, this is going to be a benefit. Lots of carbons have denuded soils, but there's going to be lots of places where messing around with the natural order is going to have some real impacts. So there's a range of things, from adding granite to soils, to these, altering crops to make more lignin production, to really far out stuff that I personally have real questions about. But the point of academic studies is to understand them, where people talk about modifying free living ocean biota to make biological materials that are kind of synthetic biology, making amino acids not found in nature so they don't break down, they just sink. I personally think that would be really a kind of radical high risk thing. I wouldn't take that seriously, but I just want to give you a sense that there's a range of things in open system carbon removal. And the goal of the effort at UChicago is broadly to bring in researchers, to collaborate with people who are pushing this on the industrial side, and to bring kind of academic rigor to understand how well they would work and then what the impacts are, and to be an interface between the regulator, the community of regulators and environmental activists as carbon removal moves forward.
We come back and sit down with you, David, in 5 years, and we do a check-in. What are you telling me of what you're particularly proud that you've been able to accomplish? What's in your mind's eye?
I hope that we really will pass the kind of torch of this research to a new generation. So I just love the opportunity of being one of the early researchers. I don't think I was necessarily particularly smart. I just think I was one of the first people really taking this topic seriously. But I'm very conscious that I and some of the other people who've done that, we're kind of locked into our ideas. And my biggest goal here is to hire a bunch of new faculty and get out of the way. And I think having a real community of faculty, if we get to a point where we've got like 5 or 10 faculty who are really hired primarily in this effort, and then a bunch of other interested faculty and networks to other universities, that's really a different and broader and more diverse intellectual world, a world that can deal with these ideas in a more serious way, and that gets it out of where it is now, where I think there's a limited set of us who've got kind of too much influence in this topic. A fact of research, especially on solar geoengineering more than on carbon removal, has been that there's individual institutions that have 1 or at the most 2 faculty. And so it's all kind of subcritical. And the idea of really getting enough faculty that we can do what UChicago has often been really proud of trying to define what the field is, maybe write some textbooks and try and say what's in and what's out, and how to think about teaching, what this thing is, how it relates to other things, to how we think about other environmental impacts or managing relationships in human and nature. This needs to fit together into a larger package in the physical and social sciences. And I think the idea of doing that really requires an intellectual community. And the goal here is to hire enough people, faculty and postdocs and long-term visitors and engineers, to build an intellectual community that really has its own life.
Big Brains is a production of the University of Chicago Podcast Network. We're sponsored by the Graham School. Are you a lifelong learner with an insatiable curiosity? Access more than 50 open enrollment courses every quarter. Learn more at graham.uchicago.edu/bigbrains. If you like what you heard on our podcast, please leave us a rating and review. The show is hosted by Paul M. Rand and produced by Leah Cesarine and me, Matt Hodap. Thanks for listening.